As most of you probably noticed in the last section or two, when we use a sequence of partial sums to try to estimate the sum for a series, sometimes finding the nth term for that sequence of partial sums is really difficult. When we are able to do it, it's mostly on geometric series and on telescoping series, but for some other types of series, it's nearly impossible, if not impossible. So for the next few sections, we're going to focus just on some different tests that we can do to decide if a series is convergent or divergent, and we're really not concerned with finding the actual sum. There are going to be a couple cases where we can estimate it, but we're really just focused here on deciding whether our series converges or diverges. In this section, we are going to learn the divergence test, and we'll also learn about p-series and harmonic series, as well as the integral test. So we're going to start with the divergence test, which is pretty simple. And as the name implies, the divergence test can only prove divergence. You can never use the divergence test to come to a conclusion that a series is convergent. We use this only to determine divergence. So for some infinite series where the terms are generated by a sub n, if the limit as n approaches infinity for a sub n is not 0, then the series automatically diverges. So let's take a second just to see what this means. In the series, we're adding together an infinite number of terms. If it converges, that means that sum eventually stops somewhere. So the only hope we could possibly have of this sum ever stopping is if we eventually stop adding to it, or the values get so tiny that they don't contribute any additional significant value to the sum. So if those terms from the a sub n don't converge to 0, that means we're never going to stop adding to this sum, which means it's going to diverge. If the limit is 0, that does not guarantee anything. It could still converge or diverge. So, like I said, we can only use this to prove divergence. You can never use the divergence test to prove convergence. So the divergence test is just a simple limit question. And anytime we see a series and we know how to find the limit for the values that we are adding, we could use this test. So my directions here are not going to be determine convergence or divergence. We're going to first figure out, does the divergence test apply? And if it does, that means we can say the series is divergent. If the divergence test does not apply, that means our limit did go to 0. So the first one we're going to look at is the sum from 1 to infinity of 2n minus 5 over n plus 1. Since we're specifically told to just use the divergence test here, all we're interested in calculating is our limit. So we want to know the limit as n approaches infinity for 2n minus 5 over n plus 1. Well, because the degrees of our numerator and denominator match, we can calculate this limit using our leading coefficients, which are 2 and 1. 2 divided by 1 is equal to 2, which is not 0. So yes, the divergence test applies. And the sum from n equals 1 to infinity of 2n minus 5 over n plus 1 is divergent. The fact that we determined that the limit is 2, that means in the long run, the value for this fraction is going to go to 2. And we're being asked to add those terms together forever. So we're going to be continually adding a value either at or very close to 2 over and over and over and over and over again forever. So if we keep adding 2, that sum is never going to stop. The sum is just going to blow up and go to infinity. So that means the series is divergent. The sum from 1 to infinity of 3 over the square root of n. We want to know if the divergence test applies and if we can definitively state that this series is divergent. Because of that, the first thing that we check is the limit as n approaches infinity of 3 over square root n. If the n values get larger and larger and larger and larger, even after we take the square roots, we're talking about n equals 10,000 or a million or 10 million, that square root value is still going to continue to get larger and larger and larger, whereas our numerator is fixed at 3. You could also think of this using that exponent test that we talked about earlier and compare exponents. The exponent or the degree of our numerator is 0. The degree of our denominator is 1/2. Since the degree of the denominator is bigger, the value for this limit is 0. The value of our terms in this sequence, 3 over square root n, will eventually go to 0. And I'm sorry, it looks like a square instead of a 0. My screen on my Surface Pro, I think, is not fixed. So because we got a 0, remember the divergence test says if the limit is not 0. So that's not what we found, so the divergence test does not apply here. And we cannot definitively say whether this series will converge or diverge. And we'll actually learn later in this section that this particular series does diverge, but we just can't use our divergence test to prove that. So we cannot use that test on this particular series. So this series is actually called a p-series. And a p-series is a series of the form sum from 1 to infinity of 1 over n to the p. So remember, n is the index here. It's like the variable. So it's very important that it is in the denominator and it's the base of that exponential piece. P will be a number. And based on the value of P, we can say whether this particular series will converge or diverge. So the P-series test, if you recognize that you're being asked to find convergence or divergence of a P-series, the sum from 1 to infinity of 1 over n to the P converges if P is greater than 1. It cannot equal 1. If it's strictly greater than 1, then this will be a convergent series. It diverges if P is less than or equal to 1. So revisit that example that we just saw in the divergence test. Is the sum from 1 to infinity of 3 over square root n convergent or divergent? Now that 3 in our numerator makes no difference whatsoever when it comes to convergence or divergence. And we really could, if we wanted to, pull that 3 out front and just kind of ignore it until the end. Whether or not 1 over square root n converges or diverges is solely based on the structure of this sequence, and if it diverges, then multiplying by 3 will still make it diverge. If it was convergent, which means we get a finite answer back for this sum, then taking that finite answer and multiplying by 3 is still a finite answer. So that times 3 really doesn't mean anything in terms of finding convergence or divergence. So for this one, we need to see it written as n to a power. So we would rewrite this as 3 times the sum from 1 to infinity of 1 over n to the half. So we're dealing with a P-series with P equal a half. And since a half is less than or equal to 1, that's our test. Either it's greater than 1 or it's less than or equal to 1. That means this particular series is divergent. Now, you might notice that I use diverges and divergent interchangeably, and that's perfectly fine. They mean the same thing. So it's all just because of that exponent. N has to be in our denominator, and then it has to be the base with some numeric exponent so that we can use our P-series test to prove convergence or divergence. And this particular series diverges. What about the sum from 1 to infinity of -2 over n cubed? This is also a P-series. We have n in the denominator and n is raised to some numeric power. The -2 really doesn't matter. Just like in the last example, we could pull that out front and just kind of ignore it because it will not change the fact of whether 1 over n cubed converges or diverges. So this is a P-series, and we're dealing with a p-value of 3. 3 is greater than 1, and our test up here states that if you have a p-value that's greater than 1, the series will converge. Now, all of these P-series, if you were to do the divergence test on them, they would fail the divergence test because all of these sequences that we're using have a limit of 0. The problem is they must approach 0 very quickly in order for that sum to eventually be cut off somewhere. So square root of n, what we're saying here is it does go to 0, but it does not get there quick enough. Because it just kind of meanders and slowly goes to 0, that extra time it takes for the values to get smaller and smaller allows our sum to accumulate to infinity. But n cubed in the denominator, those overall values of 1 over n cubed are going to get smaller much, much quicker. And because of that, we're able to cut this sum off pretty quickly and allow it to eventually stop somewhere. And that's what makes it convergent. So there's a special type of series called the harmonic series. And the harmonic series is specifically the p series when p equals 1. So it's the sum from 1 to infinity of 1 over n. So we don't see a power there. So hopefully you remember from algebra that when there's no power written, it's just assumed to be a 1. So since the harmonic series is a p-series, if you look back to how we determine whether a p-series is convergent or divergent, here because p equals 1, a harmonic series is divergent. 1 is really that, that deciding point. Anything less than or equal to 1 will diverge, but anything greater than 1 converges. So that value of 1 is really, really important. And that's our harmonic series when it's equal to 1. This is a divergent series because p equals 1. The word harmonic may be familiar to most of you. Harmonics come up in physics when you're studying sound, and harmonics are also very important in music. And they have to do with the length of a sound wave being a multiple of the first harmonic wave. So it's very easy to take the first harmonic wave of 1 and create the terms in the series by just doing multiples. The final test that we're going to learn in this section is called the integral test. And it's very similar, or at least we could take all these p-series that we just learned about, and we also could solve them using the integral test. Oops. So finding the sum of an infinite series is very similar to calculating an improper integral that goes off to infinity. If we want the sum from 1 to infinity of a sub n, and a sub n can be written as a function as f of n, we could draw that function, and the only restriction is with sequences in series, we have to only use whole number values of n. So if we start at 1 and work our way up, technically what we're doing here is to find the area, we're going to figure out the value of our series. So this is a sub 1, this is a sub 2, this is a sub 3. So if we use those as the heights of our rectangles that have a width of 1, then every rectangle here will have an area that's represented by the term in the series. So this rectangle right here, the area is the base, which is 1, times the height, which is a of 1. So we just get the first term, a of 1. If we do that for all of them, this next rectangle would have a height of a sub 2. The following rectangle would be a sub 3. So we can estimate these sums very similar to how we do a Riemann sum in Calculus 1 when we're first learning about definite integrals. So this example uses left endpoints. Because it's a decreasing sequence, the left endpoints are always going to overshoot the actual area underneath. If we were to use right endpoints, these areas would always undercut the actual area, and the exact value is somewhere in between. But if this area using an integral were to converge, we know that the value is somewhere in between those. So they will always converge or diverge together. They'll always do the same thing. So if we recognize that a sub n as something that we know how to integrate, the integral test says the sum from 1 to infinity of a sub n and the integral from 1 to infinity of f of n dn, where a sub n can be written as a function f of n, will always converge or diverge together. Now, even when we don't use the Riemann sum and we just use the exact area using our improper integral here, that still might not be the exact same answer as our series, but it's a pretty good estimate. So if you ever are asked to find the convergence or divergence of a series that is something you recognize how to integrate, you can always use the integral test. So we're going to try this out first on a p-series. The p-series have their own special rules, but all of the p-series can also be determined to be convergent or divergent using an integral test. So let's try our harmonic series first, which was just 1 over n. We can show with an integral that this harmonic series is divergent because it's going to do the same thing as the integral from 1 to infinity of 1 over x dx. 1 over n and 1 over x represent the same values. We're just using a different variable or index. So the integral for 1 over x is natural log of x. And when we evaluate that, we have to evaluate the infinity as a limit. So one of the limit as x approaches infinity for natural log of x. And then we subtract what we get when we plug in our lower bound. Natural log of 1 is 0. So really, it's all dependent upon that limit. We want to know what is happening on the natural log graph as x approaches infinity, and you can just take a look at this graph and see that as the x values approach infinity, the y values also approach infinity. They don't grow quite as quickly as the x values do, but nothing ever stops them from growing. There's no horizontal asymptote that's going to make them level out. So that tells me that this is divergent. Another p-series, the sum from 1 to infinity of 5 over n cubed. Well, if you remember the p-series test, we will know right away whether this is convergent or divergent. But if for some reason you forget, we can always integrate 1 to infinity 5 over x cubed dx. Now, in order to find that antiderivative, we're going to have to pull x to the numerator with a negative power. Then we can do the power rule on it. So we'll write it as 5x to the negative 3. So the power rule says add 1 to your exponent and divide by that new exponent. We get negative 5 halves x to the negative 2 from 1 to infinity. Or negative 5 over 2x squared from 1 to infinity. So infinity always has to be evaluated as a limit. And then we subtract what we get when we plug in our lower bound, which is 1. If you plug 1 into negative 5 over 2x squared, you get negative 5 halves. Now, if you take a look at this limit, you can use the power rule we talked about. The degree in the numerator is 0. The degree in the denominator is 2. Since the degree in the denominator is larger, this limit is going to go to 0. So we've got 0 minus negative 5 halves is really positive 5 halves. So we're able to get a finite answer for this improper integral. Any finite answer indicates that it is convergent, and our series will always do the same thing. So if the improper integral is convergent, that means the series is also convergent. Now that doesn't mean our sum is 5 halves, although 5 halves is a decent approximation, depending on how exactly the overage and the underage that we're going to have might throw it off just a tiny bit. So let's try one more really quick that is not a p-series. We're going to try to determine if the sum from n equals 0 to infinity of 4 over n squared plus 9 is convergent or divergent. Now, if that plus 9 wasn't there, this would look like a p-series. But because of the plus 9, we can't exactly use the p-series rules on this. For a p-series, the only thing you want to have in your denominator is the n with the power. Although we could make a guess here that, well, if the plus 9 wasn't there, this would be a convergent p-series. That plus 9 in the denominator is only going to make our denominator get larger even quicker, which makes the overall values of this fraction smaller quicker. So we could make an educated guess here and say that this is probably convergent, but we're interested in actually proving it, and this is something that I recognize how to integrate. So I can set up a definite integral. We want to use the exact same bounds that the series uses. And also the fact that this one starts at 0 instead of 1 is not going to have any bearing whatsoever on whether the series converges or diverges. If you determine that an infinite number of terms goes to infinity, just subtracting one of them off or including an additional one is not going to change that fact. So convergence and divergence has nothing to do with the bounds here on your series or your integral. And I'm actually going to change this. I prefer to use x here. So you might have remember seeing this in our last chapter. Anytime you have a sum of squares in the denominator and a constant in the numerator, the antiderivative is arctan. It's also on the calculus reference sheet that we have posted on our Moodle page as well. So I know from that formula on the reference sheet, this is going to be 4/3 arctan or tan inverse, whichever you like, they're the same thing, of x over 3. And we want to evaluate from 0 to infinity. The infinity portion has to be evaluated as a limit. So the limit as x approaches infinity for 4/3 arctan x over 3. and then we'll want to subtract what we get when we plug in 0. So 0 in that fraction will just be 0, and arctan of 0 is 0. You do have arctan on your calculator. It's equal to it's the same thing as tan inverse. Arctan is the same thing as tan inverse. This first one, however, you can't really do in the calculator. You have to know what the arctan graph looks like. So it looks just like one iteration of our tan graph, except since it's the inverse, it's flipped over the y equals x line. And this function has two horizontal asymptotes. As we approach negative infinity, our y values are approaching negative pi over 2. As we approach positive infinity, our y values are approaching positive pi over 2. So the limit as x approaches infinity, so infinity over 3 is still infinity. Dividing a giant number by 3 is not going to change the fact that it's a giant, giant number. Now we're talking millions and billions here. So we're still interested in the limit as x approaches infinity. Arctan of infinity is approaching pi over 2. So what we have here is 4/3 times pi over 2, or 2 pi over 3. The exact value really doesn't matter. Just the fact that we got a finite answer to this improper integral means that this series is convergent, which we suspected from the beginning because it does kind of look like a p-series with p equal to 2, but we can't use the p-series rules because of that plus 9. We've got to find another way to do it. So usually, if you look like you have a p-series, but there's just one thing off, then you can always do the integral test. Because p-series are just, they're just power functions. They're just like x to a power, and we easily know how to integrate all of those. So the last thing I want to mention real quick before wrapping up this section are just some properties of infinite series. And these may come in handy with some of the more difficult problems. And these are just algebraic properties. The first one I've actually already used once in this video. So suppose we've got some infinite series, the sum for a sub n, and it converges, and we have some constant c, which is just some real number value. Then the sum of c times a sub n, remember I said that c really could come out front and be dealt with at the end. We know that the sum of a sub n converges to a, and the c just gets carried along the same way it does when we do derivatives and antiderivatives. It's just a coefficient. It has no variables in it, so we just continue to use it as we go from step to step. So if our sequence, or if our series of a sub n converges to a, then we really could multiply by anything we wanted to, and it would still be convergent, and we would multiply by the sum by that same constant or coefficient. This second property I have not used yet, but it may come in handy later. Suppose the sum of a sub n converges to a, and the sum of some sequence b sub n converges to b. So we know what these guys do separately. Then, if we were to take those two sequences and combine them, either with addition or subtraction, it would still be convergent, because we could technically separate them into their own separate sequences using the same operation between. And we can get the sum just by using what we know to be the sum of them individually. So if we've got a series that has multiple terms, we really can evaluate that series one term at a time, the same exact way we do derivatives, the same exact way we do antiderivatives. If our terms are separated with addition and subtraction, we can work with each one individually. Now this last property I've also used and explained already. If m is a positive integer, then the sum from n equals 1 to infinity for a sub n, and the sum from n equals m to infinity for a sub n either converge or diverge together. They will always do the same thing. And I used this in one of our last examples where I said the starting value of your n makes no difference whatsoever on determining whether this series will converge or diverge. So you may see some definitions or some theorems, and they say that your series starts at 1, but then you're asked to do a problem where the series starts at 5. That series will still do the same exact thing in terms of convergence or divergence if it were to start at 1. So don't let that starting value on the n trip you up. You really can ignore it. The only time it's really important, like we said back in geometric series, if we want to define the exact sum of a geometric series, then that starting value on n will matter. It won't make a difference on whether it converges or diverges, but it will affect the exact sum.